Have you ever wondered if a black hole, one of the most enigmatic cosmic entities, could truly consume the entire universe, relentlessly swallowing stars, galaxies, and everything in its seemingly unstoppable path? These mysterious cosmic entities possess gravity so intense and powerful that nothing, not even light itself, can escape their grasp once it crosses a certain boundary known as the event horizon. Black holes form from the remnants of massive stars that have collapsed under their own gravity or from the dramatic collapse of vast gas clouds, and they exist in various sizes scattered throughout the vast cosmos. From relatively small stellar mass black holes formed from single stars, to intermediate ones, and enormous supermassive ones at galaxy centers, they are incredibly diverse in their origins, scales, and influences. Supermassive black holes, often abbreviated as SMBHs, reside at the centers of most galaxies, including our own Milky Way, boasting masses that are millions or even billions of times greater than our Sun. One of the key components of a black hole is the event horizon, the critical boundary and point of no return, beyond which escape becomes utterly impossible for anything, including light. Deep within the black hole lies the singularity, a central point of infinite density and zero volume, where the known laws of physics completely break down and our understanding fails. Often surrounding the black hole is a spinning accretion disk made of superheated matter and gas, which emits intense radiation, including X-rays, as it spirals inward toward the event horizon. Despite their immense power and fearsome reputation, black holes are not cosmic vacuum cleaners that suck in everything nearby. They only capture objects that venture dangerously too close to their event horizon. For instance, if our Sun were to suddenly transform into a black hole while keeping exactly the same mass, Earth's orbit around it would remain completely unchanged, as gravity depends on mass and distance, not size. The universe's ongoing expansion, primarily driven by mysterious dark energy, constantly increases the vast distances between celestial objects like galaxies, stars, and black holes themselves. This relentless cosmic expansion makes collisions or mergers with black holes far less probable over time, effectively acting as a natural barrier preventing their universal consumption. For black holes to merge frequently and grow significantly by consuming vast amounts of surrounding matter, the universe's expansion would need to dramatically reverse into a contraction, which current models do not predict. Furthermore, black holes have inherent physical limits to their growth and size, preventing them from expanding indefinitely or becoming infinitely large through accretion. Theoretical models and simulations suggest that actively accreting supermassive black holes reach a maximum mass limit of around 50 billion solar masses due to feedback mechanisms and inefficient feeding. Beyond this critical point, they would struggle to accrete enough surrounding matter and gas to continue growing further, effectively capping their maximum possible size. Intriguingly, black holes are not eternal fixtures in the cosmos. They gradually evaporate over immense timescales through a subtle process known as Hawking radiation. This groundbreaking quantum effect, first predicted by physicist Stephen Hawking in 1974, causes black holes to emit particles from just outside their event horizon, slowly causing them to lose mass, shrink, and eventually disappear completely. Remarkably, the evaporation rate is inversely proportional to the black hole's mass, meaning smaller black holes evaporate much more quickly while larger supermassive ones take vastly longer. So, while a stellar mass black hole might take billions of years to fully evaporate, an enormous supermassive one could require quadrillions or even longer timescales to completely vanish. Black holes themselves are completely invisible to direct observation, detectable only indirectly through their profound gravitational effects on surrounding matter, stars, and the bending of light. Near a black hole, extreme time dilation occurs due to intense gravity, meaning time passes much more slowly for an observer closer to the event horizon compared to someone far away. Any objects daring to fall into a black hole would experience the dramatic process of spaghettification, where intense tidal forces stretch them vertically and compress them horizontally into long, thin strands before tearing them apart. Despite their fearsome reputation, black holes have a limited range of gravitational influence, much like any other massive object, affecting only nearby matter significantly. The nearest known black hole to Earth, part of a binary system, is approximately 1,500 light-years away, placing it at a very safe and immense distance from our solar system. In conclusion, while black holes are undeniably powerful and awe-inspiring cosmic entities, the universe remains perfectly safe from being entirely consumed or devoured by them. The continuous expansion of the universe driven by dark energy, their inherent growth limitations around 50 billion solar masses, and their eventual evaporation via Hawking radiation all conspire to prevent them from devouring the entire cosmos. So rest assured, the universe will continue its grand, majestic journey through time and space, far too vast, dynamic, and resilient for any single black hole, or even many, to conquer and consume entirely.